This time, I'm going to talk about normality tests in Python. Let's review the assumptions for multiple linear regression first. The first assumption is the linear relationship. If the relationship is not linear, you might want to convert the variables into a linear relationship or use another regression model. The second assumption is homoscedasticity. That is, the variance of the residues should be the same at each level of the independent variables. Third assumption is independent errors. The fourth assumption is there's no multicollinearity in the model. That means there's no highly correlated independent variables in the model. I discussed this assumption in my previous YouTube video. You're welcome to watch it. The last assumption is normally distributed residuals. In this video, I will discuss this assumption mainly. Then what is normality test? Normality tests are used to determine if a dataset is well modeled by a normal distribution. When we check the normality of residuals, we need to remember we only check the residual for normality. We don't need to check for normality of the raw data. Our dependent and independent variables do not need to be normally distributed in order to fit a linear regression model. So, what are the consequences associated with a violation of normality assumption? Violation does not contribute to bias or inefficiency in regression models. It is only important for the calculation of p-value for significance testing. Also, when the sample size is large enough, we can consider the distribution of this error term to be normal. Then how do we check normality? There are many methods to test normality. I will mention several are used in this video. First, QQ plots. Then, the Shapiro-wilk test. And then the Anderson-Darling test. And then the KS test. And then Agostino's KSquared Test. Let's review each method. So, what is QQ plots? The QQ plots is a short abbreviation for quantile-quantile plots. It's a graphical tool to help us assess if the set of the data came from some theoretical distribution, such as normal or exponential distribution. It does not give us a number, but it shows us visually to let us to check if the assumption is correct. This is a typical QQ plot. On the horizontal axis, we have this theoretical quantile. On the vertical axis, we have sample quantiles. You can imagine if the theoretical distribution is the same with the sample distribution, and then this QQ plot will show a straight line because the theoretical quantiles is exactly the same with the sample quantiles. Then What is Shapiro-Wilk test? First, we have the sample data, say from x1, x2 to xn. Then we need to sort them in the increasing order. And sorted sample will become y1, y2, and to yn. And then we will calculate the sum. If we divide this by n-1, that will be the variance of the sample. So this sum describes the variation of this sample data. And then we calculate B. So how do we calculate B? The B is calculated with this formula. First, it will take the difference from this sorted sample data and then times A. The A came from this Shapiro-Wilk table. You can see in this table we have the sample size here. For example, if you have a sample size 32, you need to check this column. And A1 is this number, and in the middle A16 is next number. So basically we will calculate this Shapiro-Wilk table based on our theoretical distribution. So we can say the data in this table do the magic. After we calculate B, and then we can calculate the test statistic W equal to B squared divided by S squared. If the test statistic W is smaller than the critical threshold, the assumption of a normal distribution has to be rejected. That is, our sample distribution is not a normal distribution. I'm going to show you how to implement this Shapiro-Wilk test in Python later. Then, what is Anderson-Darling test? Anderson-Darling test can be used between any two distributions. First, we have our theoretical distribution f, and then we have our empirical cumulative distribution function fn. We will take the difference between our empirical distribution and our theoretical distribution, square it, and times weight, and calculate the sum. When the weighting function wx is 1, the statistic is called Kramer-1-Mises statistic. And for Anderson-Darling test, we use this as our weighting function. That is, the Anderson-Darling distance places more weight on observations in the tails of the distribution. Because we are calculating the difference between two distributions, you can imagine if the two distributions are the same or are close enough, we should get a squared very small, or even equal to 0 if the two distributions are exactly the same. Next one is KS test. KS test is similar to Anderson-Darling test. It tests the difference between two distributions. In this graph, you can see the red line is the cumulative distribution function of a theoretical distribution, and the blue line is our sample distribution. And the difference between two distributions is our KS statistic. Next one is Agostino's K-squared test. For this Agostino's squared test, we consider samples kurtosis and skewness. If the skewness of this distribution is G1, kurtosis is G2, and then we can convert skewness and kurtosis based on this formula and get Z1 and Z2. I got this formula from Wikipedia. If you want to know the detail about this formula, about why we use this for the transformation, you can go to the Wikipedia to view the detail. After we transform the skewness and the kurtosis, and we square them and sum those up, and this will give us the K-squared test score. You can see if the skewness and the kurtosis are all close to 0, we will get a very small K-squared. Please remember this Agostino's K-squared test only focus on kurtosis and skewness. In my previous video, I developed a model to predict GDP growth based on the following 5 factors. It is showed on YouTube under this title, Multicollinearity and its detection in Python. You are welcome to watch this video. In this video, I'm going to use the same data for this normality test. Now let's see how I did normality test in Python. If you want to know how I got the data and how I built the model, please watch my previous video on YouTube. First, let's see what we got for the data. GDP is our dependent variable, and we have all those independent variables. And then I built the model without consumer credit, as I discussed in my previous video. And then let's review the summary of my model. For the R-squared, we got 96.2%, and adjusted R-squared is 96.1%. And then you can see here the skew is 0.785, so it's moderate skew in this model, and the kurtosis is 3.392. As you know, the kurtosis for normal distribution is 3, so it is close to the normal distribution from this kurtosis. And next one, let's do the plot for the residue. You can see the mean of the residue is very close to 0, and the variance is this number. And from the graph, you can see this doesn't look like a normal distribution. It has a bump here for the residual. And next one, let's do the QQ plot. As I mentioned with my PowerPoint, you can see the theoretical quantile is on the horizontal axis, and that the sample quantiles is on the vertical axis. If it follows normal distribution, it should follow this straight line. But you can see the plots are not following straight line. But as I mentioned, the QQ plot doesn't give an exact number for you to evaluate. Then let's use our normality tests I mentioned. First, let's check the Shapiro-wilk test. You can see if we say the alpha is 5%, and then the sample does not look normal. So our non-hypothesis is it is normal distribution, but now we have to reject this non-hypothesis. The next one, let's check our Agostino's K-squared test. Also, with alpha 5%, the sample does not look normal. How about next test, the Anderson-Darling test? So for the Anderson-Darling test, we give different confidence intervals, but all failed the test. All shows data does not look normal. How about next one, the KS tests? And we also got the same conclusion. The sample does not look normal because this statistics is very big. So we run the Shapiro-wilk test, the Anderson-Darling test, the KS test, and also Agostino's K-squared test. They all give us the same conclusion. The model residue does not follow a normal distribution. So how about we do a test with dummy data which does follow normal distribution? See what happens. Now, I generated some dummy data with Python from normal distribution, and then I will run the test for those dummy data, and let's see what happens. You can see the Shapiro-wilk test says the sample looks normal, and also Agostino's K-squared test says sample looks normal. For Anderson-Darling test, for all different confidence levels, we got the same conclusion, data looks normal. And also for the KS test, we also got conclusion, sample looks normal. If you check the QQ plots, you can see almost all the dots follow this straight line. That means our sample distribution is the same with the theoretical distribution, that is, the normal distribution. This is how I did normality tests in Python. Please provide your comments and subscribe to my channel. Thank you for watching.